Hello students, welcome to Educate. We are going to continue with the numericals of ray optics. So let's start question number 9.10. Question says, what is the focal length of a convex lens of focal length 30 cm in contact with a concave lens of focal length 20 cm? Is the system a converging or a diverging lens? Ignore thickness of the lenses. So you have studied when lenses are in contact, then how to write the combined focal length. So for that, we write 1 upon f equals 1 upon f is equal to 1 upon f1 plus 1 upon f2, right? Here we are given f1 means focal length 30 centimeter, which is convex type. So f1 is equal to plus 30 cm and f2 is equal to, this is concave lens, so focal length will be minus 20 centimeter. Now if we put them in contact, so 1 upon f will be equal to 1 upon 30 plus 1 upon minus 20. So LCM will be 60. This will be 2. This will be minus 3, which gives minus 1 upon 60. From where we get f equal to minus 60 centimeter. Since f is negative, it means system is behaving like a here this is negative. Negative means concave lens or diverging lens. So here we have got our answer. So answer is diverging lens, right? Now let's see next question. Next question says, a compound microscope consists of an objective lens of focal length 2 centimeter. So we are talking about compound microscope. So here basic information, we need FO, FE, focal length of objective. So here objective of focal length 2 cm. So this is 2 cm and eyepiece has focal length 6.25 cm, right? Separated by distance of 15 centimeter, length of the tube or separation between the two lenses is 15 centimeter. And how far from the object should an object be placed to obtain the final image at least distance of distinct vision? So we wish that we should be 25 centimeter, although it will be negative, so that we will take into consideration. And the second case is when final image is formed at infinity, and what is magnifying power of the microscope in each case. So we can do the calculation easily. So let's do the calculation for eyepiece first. So in case of eyepiece, we can apply the formula for eyepiece. 1 upon FE is equal to 1 upon VE minus 1 upon UE, right? And we are given VE as minus 15 centimeter, FE is 6.25, so we can write it 1 upon 6.25 equal to 1 upon minus 25 minus 1 upon UE. We can take this UE to this side. So 1 upon UE is equal to 1 upon minus 25 plus 1 upon, not plus, this will go to this side. So this will again become minus, so minus 6.25. So we can evaluate, just take 1 second to evaluate it. So this will come out to be minus 5 centimeters. This is first case. Now, distance of image from objective we can find. Distance of image from objective. So since their separation is given as 15 centimeter in our question, so here it is at 5 centimeters, so reduce 5, so we will get as 10 centimeter. So this will become in magnitude 15 minus 5, that is 10 cm. Right, up to here I think thing is clear. Now for objective, let's apply the formula 1 upon FO 1 upon VO minus 1 upon UO. Here VO we have found as 10 centimeter, right, and that will be have, this is VO, and we have to find out UO. We are given FO also. FO is 2 centimeter in our question. Here it's given 2 centimeter, so we can write, so it will become 1 upon 2 equal to 1 upon VO. VO is to that side, it will be 10 minus 1 upon UO. So from here we can get 1 upon UO equal to 1 by 10 and minus 1 by 2. So we can evaluate it. So this will become minus 2.5 centimeter. Minus 2.5 centimeter. Here reverse, which is equal to UO. Correct? I think up to here thing is clear. Now what more do we need? Here next point is, they are saying that we have to find out VO also. So we have got UO here, that is minus 2.5 centimeter, right, and then we have to find out magnifying power. So magnifying power, what is formula? Magnifying power, M is equal to MO multiplied by ME, and ME simple magnifying glass, and MO is VO upon UO. So we can put the values, VO upon UO times 1 plus D upon FE. D is least distance of distinct vision, which is given as 25 centimeter. So other values we have obtained. We can put the values, and hence we will get value as 20. Right? Other values we have evaluated what is VO and what is UO. So you can put, and FE is also given in our question. And in second case, when final image is formed at infinity, then what happens? So when final image is formed at infinity, then V equal to infinity, 1 upon F equal to 1 upon V minus 1 upon U. This will give 1 upon F equal to minus 1 upon U. Right? So from here we get, if we are considering it for eyepiece, so we can say FEE is negative of UE, right? So we can get the value of UE as minus 6.25 centimeter. So this will become minus, so UE equal to minus 6.25 centimeter. So up to here thing is very clear. Now separation is given as 15 centimeter. So again we need distance of image from objective. So just to reduce this value from 15, so 15 minus 6.25. So this will become 8.75, right? So this is 8.75 and this will be image distance for objective. Situation is like this. This is objective, this is eyepiece. So here image is formed and so 8.75. Now we are given FO equal to 2 cm and this will be VO, right? So we have to find out UO. So we can evaluate so let's apply the formula 1 upon FO equal to 1 upon VO minus 1 upon UO, and here VO is given and FO is given, so 1 upon 2, FO is given as 2 centimeter, right? So 1 upon VO, we have got as 8.75 minus 1 upon UO. So we can evaluate UO this time again. So UO will be minus 2.59 centimeter, minus 2.59 centimeter. Now what is left? Magnification again, M equal to MO into ME. So this will be VO upon UO, and here it will be just D upon FE. Putting the values of VO, UO, D and FE, we will get 13.5. Answer will be 13.5. You can do the calculation. It's simple. Now let's go to next question. Now what is next question? Next question says a person with a normal near point using compound microscope with objective of focal length 8 millimeter and eyepiece of focal length 2.5 centimeter can bring an object placed at 9 millimeter from the objective in sharp focus. What is separation between the two lenses? Calculate the magnifying power of the microscope. So let's evaluate it. We are given focal length of objective is given as 8 millimeters. So we can write it 0.8 centimeter, right? And then UO is given, so object distance eyepiece, this is 9 millimeter. So UO is minus 0.9 centimeter, right? And now we have to find out VO. So VO can be determined using a lens formula 1 upon FO, 1 upon VO minus 1 upon UO, or 1 upon VO is equal to 1 upon FO plus 1 upon UO. We can put the values 1 upon FO 0.8 plus 1 upon minus 0.9, right? So we can evaluate. Just give 1 minute to find its answer. So this will give 7.2 centimeter. So we have got VO. Now further, for eyepiece, let's consider the situation. So for eyepiece, FE is given. What is FE? So this is component with objective focal length. Eyepiece has focal length 2.5 centimeters. So 2.5 cm, and other information is given. Final image is formed at least distance of distinct division. So we can say VE equal to minus 25 centimeter. Right. Now we can easily evaluate UE. So 1 upon FE is equal to 1 upon VE minus 1 upon UE. Our concern is to get UE. So 1 upon UE will be in the left. 1 upon, let's write it, minus FE and plus 1 upon VE. Let's put the values. So minus 1 upon 2.5 minus 1 upon 25. We can evaluate. This will be 25. This will be minus 10 minus 1. Right. So we can get UE as 25 divided by minus 11. 25 divided by minus 11, which will be minus 2.27 centimeters. Right. Now, separation between the two lenses can be found by VO plus UE. So, separation between the two lenses will be equal to VO plus modulus of UE. So modulus of UE, this thing, and the VO we have got at 7.2. So just write 7.2 and plus this value 2.27. So that will be 9.47 centimeters. Right. Now we have to find out magnifying power. So magnifying power can be found by using formula. You remember? So what is magnifying power? So formula is M equal to MO into ME, which can be written as VO upon UO 1 plus D upon FE, right? So we have all values, we can put them. So it will be 7.2 divided by UO. If we take modulus value, then it will be 0.9. 1 plus this is 25 divided by FE. FE is 2.5. So this will give, this is 8 times and this is 10 times. 8 multiplied by 11, which is 88, right? So I think you have understood. Now let's take next question. Now what does next question say? sorry. A small telescope has an objective lens of focal length 144 centimeter and an eyepiece of focal length 6 centimeter. So we are talking about telescope. Here f objective is given, f eyepiece is given. F objective is given as 144 cm and f eyepiece is given just 6 centimeter, right? And what is magnifying power of the telescope? We have to find out. It will be the ratio of the two and then separation. Okay. So magnifying power we can find. So M is given by FO divided by FE. So 144 divided by 6. So it will give 24. Now, second part says we have to find out what is the separation between the two lenses. So, separation between the lenses, L is FO plus FE. Just put the values. 144 plus 6, so 150 centimeter. So this is the answer. Now let's consider next question. What does next question say? Next question says a giant refracting telescope at an observatory has an objective lens of focal length 15 centimeter. So FO is given as 15 centimeter and objective, sorry, it's 15 centimeter. If an eyepiece has focal length 1 centimeter, FE is 1 cm. What more information is given? What is angular magnification of the telescope? Angular magnification is to be found. Angular magnification. Okay. This is the first part. So let's evaluate it. So what is angular magnification? So angular magnification is given by FO divided by FE. I have read the question wrong. Here it is 15 meter, not centimeter. This is 15 meter, right? So now let's write the value of FO. So 1500 centimeter divided by 1 centimeter. So this gives 1500. So answer to first part is 1500. Now second case is, if this telescope is used to view the moon, what is the diameter of the image of the moon formed by the objective lens? The diameter of the moon is 3.48 into 10 power 6 meter and the radius of lunar orbit is 3.8 into 10 power 8 meter. So let's see what happens here. So here we can imagine this lens and then we consider this diameter of the moon and it should have been from here, but let's assume it that is passing from mid point, and here this is image, right? This angle is alpha, this angle is also alpha. This is diameter of the moon, right? And this is length of, say, lunar orbit, and this is diameter of moon. Let's denote it. This is image. This will be image distance. So here's these two triangles are similar, so ratio will be same. So we can find tan alpha. So what will be tan alpha? Tan alpha will be d moon divided by lunar orbit. So d moon divided by lunar orbit. And this will also be equal to, from here, if this image is formed at focus, so we can say d image divided by fo. D image for this distance d image, and this divided by, this is size of the image, so we write d image this, and this is focal length of the lens, divided by fo. So this is basic information that we can make use. So d is given, d moon is given, this lunar orbit radius is given, so we can write these values like 3.48 into 10 power 6 divided by 3.48 into 10 to the power 6 divided by this much, 3.8 into 10 to the power 8, right, equal to d image that is to be found, and focal length of the lens is given, right. So we put this value. So focal length of the lens will be just 15 meter because we are considering the objective. So d image divided by 15. Now we can simplify it. D image is to be found. So this 3.48 divided by 3.8 into 10 to the power minus 2 multiplied by 15, and this can be evaluated, which will come out to be 13.73 meter. 13.73 meter. It is little complicated, but I think you can easily do. Now, let's do next question. Okay. So question number 15, I am leaving for you. You can do it. And question number 16, a small pin fixed on a tabletop is viewed from above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeter thick glass slab held parallel to the table? Refractive index of the glass 1.5. Does the answer depend on the location of the slab? The question is simple. Here, relation between apparent depth and real depth is to be considered, and you know very well that real depth divided by refractive index gives apparent depth. So that condition we are going to discuss. So formula is simple. If you remember that normal shift, if we find, so normal shift is actual depth minus apparent depth, right. So actual depth is say d, and apparent depth will become d upon mu. So d we can take common, mu minus 1 divided by mu. Here in our question, information is given, a small pin fixed on the tabletop to viewed from the above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from a same point through a 15 centimeter thick glass slab held parallel to the table? So here we can evaluate. So just take 15 centimeter. The situation for we are viewing object here. Suppose object is here, this is 15 centimeter. So if we view from here, so it will seems to be raised to this height, this. So this is say t. So this is apparent depth. So here we are going to find the same thing, 15 into mu. Mu is given as 1.5 minus 1 divided by 1.5. So 15 into 0.5 divided by 1.5. This will make it 10 times, and this will become 5. So it will be raised through 5 centimeter. I think thing is clear. Now, next question. So I think it is enough for this lecture. We will continue with the next question. So in next lecture. So I think till here you have understood fully. Thank you for watching. Team Educate